Okay, ready? Okay, so my name is Charlotte Okraska, and this is my NCAPS project for the fall semester. So a little bit about me. I am currently a senior here at Sandy Creek, and my future plans, I am going to be attending UNL, and I will be majoring in biological systems engineering. My project last year, I didn't really have like a set project that I was working on. It was more just me trying to explore different career options and get a taste of what I would want to do. And so I went to the U.S. Meat Animal Research Center, and I worked with Dr. Brian Woodbury. He was my mentor. And I also worked a little bit with Dr. Bobby Stromer. She was a chemist that he was working with. And I learned about the different projects that they do at the Research Center, and the main project that they were working on was antibiotic resistance. And so I learned about the different pathways that antibiotic resistance enters the environment and how it can travel throughout the environment and then the effects it has. And that brings me to this year. So this year my project was kind of split into two parts. The first part was what an environmental engineer would have to do in the field, and the second part was what an environmental engineer would do in the lab. I just really wanted to get like a taste of what a person in this job would have to do. And these are the dates that I went to the Research Center. In the beginning, the first couple meetings, we just reviewed the information and made sure I remembered everything. We set up a plan for the semester, and then once we had gotten through all of that, I was able to do labs, and we met a total of 7 times. So the first part is in the field, and so out in the field, what would an environmental engineer have to do? And one of the things is conduct an environmental impact statement. And what is an environmental impact statement? An EIS, for short, is just a document that lists all the positive and negative effects that would happen to the environment. Like, say, for example, if a company wanted to expand, they would hire an environmental engineer to come in and say, how is it going to affect the environment? Say they want to build another factory. Is it going to pollute the groundwater or cause leaks? They just need to watch pollution, make sure that the environment is not damaged. Another thing that an environmental engineer would be called to do is remove contaminants. And so my example for this situation is if a train derails and causes a chemical spill. If the chemical was dangerous, it would need to be removed. And the goal of an environmental engineer is to maintain the environment. You want to protect the environment and make sure that it's in balance. And some things you have to look at are what is pristine. The environment is not static. It's always changing, and it's different from place to place. So if you're trying to remove a certain chemical, it's going to be different for every place. And you need to consider the chemical that you're going to be removing. Is it natural? Is it man-made? Because one large aspect of removing it is you need to consider the cost and how effective it's going to be overall. And so now you have this contaminant, but how are you going to remove it? Geophysical remote sensing. So geophysical just refers to the land, and remote sensing is the use of technology to collect data over a distance. And so the remote sensing there's many different types, but the one that I was introduced to was electromagnetic induction, or EMI for short. And electromagnetic induction just works, it uses magnets to create a magnetic field, And then this magnetic field sends frequencies down to the ground, and salt is conductive, and so it'll send frequencies back. And so I got to drive an ATV around, and it had a GPS hooked up to the front of it to get your exact location, and it had the EMI on the back of it to measure the frequencies. And so I just drove it back and forth around this field to measure the salt content in the ground. And when you're doing remote sensing, there's a lot that you need to consider. Two of the main things are geography and soil composition. Geography is very important because the reason that you're measuring the salt content in the ground is because water carries salt, and if the contaminant that you're looking at is also carried by water, it's going to be collected where the salt is. And so say the area that you're looking at is in a valley. Well, because of the geography, the highest concentration is going to be at the bottom. And if the area that you're looking at is a hill, then you're not going to have a lot at the top because the water is just going to run off to the sides. And you also need to look at the soil composition because the way the soil is, it can change how the salt travels through the ground. And so the EMI, it gathered all this information, and then there was a software that generated 12 data points. And these data points were all distant from each other. And so these were points in the field that were statistically different from each other. The 12 points ranged from really low measures of salt content to really high. And so the 12 points were spread as far apart as they could. So you had the low one, the ones in between, and the high one. And then they're also physically distant from each other. And they had to be physically distant from each other because, say, there was a nail in the ground and it messed up the reading. So if you have these two readings that are like 5 inches apart, then it's not going to be accurate. And so once we have those 12 data points, we went out and took a soil sample. And then once you figure out the salt content and the chemical content of that soil sample, you can generate an equation relating the two and figure out where the chemical is located within that area. And here I have a picture of it. So this is what it looks like when you color code it. The red and orange numbers are really high, and the blue and green ones are the lower ones. And this is an example of why you need to consider the geography, because there's actually a ditch with water that runs through the bottom slanted portion. And because of that, and it was angled, so that's why it's orange along that edge, because that's where all the water was. And it had a higher elevation in the middle. And so once you, I'm going to go back to the other picture too. And so those black dots are the 12 data points. So those are physical locations out in the field, and we would go and take a soil sample. And so moving on. So this is Dr. Woodbury taking a soil sample, and this was the equipment that we used. It is like a plastic tube, and it can go 4 feet down to the ground, and so you stick it within a metal tube and it just hammers it all the way down into the ground. And I have another picture, and that just shows how far down it goes. And so the next portion of my project was in the lab. So you generate the equation to figure out the chemical or whatever's in the ground, but now you need to know how to remove it, and that is what you figure out in the lab. So antibiotics are the main thing that they're working on right now, and tylosin is the specific antibiotic that they're looking at. And excessive antibiotics are bad for the environment and human health and animal health, so we need to remove them. And one of the ways to remove them was by chemically binding the tylosin to clay and diatomaceous earth. And there are 3 types of diatomaceous earth that we looked at, and we tested each one to see which one could remove tylosin the best. So there is the raw one, the chemical one, and the pool kind. And their like actual names are on the right, but we just call them the ones on the left for simplicity. So the first one was the raw diatomaceous earth, and diatomaceous earth is just earth that contains all these dead marine organisms that lived a long, long time ago when everything was covered in water, and they died, and now they're just a part of the soil. And this kind was from Canada, and it was composed of 20% clay, 3% organic material, and the rest is silica, which is what the diatoms are made up of. And this one we found this one to bind to tylosin the best because they think it goes in between the sheets of clay and gets stuck there. And the particles have a coating of organic material, and this is a problem because it doesn't bind as well. And so in order to remove the organic material, you would rinse it with hydrogen peroxide first and get it to bind better. And then I have pictures of it. It's really small, the particles, compared to the other two types. And I think it's really pretty. I stared at it under a microscope for like over an hour. So the next kind is the chemical kind. And this one is still raw. It's just from a chemical company, so that's why it's called that. And it's not as processed as the pool grade, which is the next one I'm going to talk about. And this one had a low to like non-existent amount of organic material, and it had a low amount of clay. And so even though it's raw, just like the first kind, the regional differences account for the different composition. And this one binds better than the pool grade, which I'll be talking about next, but it does not bind as well as the raw, which is the first one. And these are some pictures of it. Okay, so that brings me to my last type of diatomaceous earth that we looked at. This one is just diatomaceous earth, no organic material, no clay. It's very processed. It was heated up, and this one is larger than all of the other ones when you see the pictures. Because it was heated up, they kind of glob together. It has a highly organized structure, so because of this, the binding sites have been changed so the tylosin doesn't bind to it like at all. It's useless, but it's really pretty. So the takeaway from this project, Dr. Woodbury really wanted me to focus on critical thinking. The science is going to change. New information is always being found, but critical thinking is a skill that I'm going to use for the rest of my life. I learned how to approach complex problems. You need to break the problem down into manageable steps and identify what you can control and how you can fix that. And I also learned to question everything for myself, not to be critical and distrustful, but because in this day and age with so much information and it being spread so rapidly, you need to take a moment and think for yourself because it's very easy to manipulate information. And for prep beyond school, I feel after hearing personal stories from Dr. Woodbury and Dr. Stromer, I feel way more prepared for college. I had the opportunity to work in the lab and do chemistry experiments, and I just feel more comfortable opening myself up to new experiences and new ideas. And also my own personal experience from this, I just feel more comfortable. My plans next semester are to continue my mentorship with Dr. Woodbury and going to the research center. I want to keep working on my current project. I'm probably going to be more in the lab looking at how it chemically binds because it's going to be cold, so I don't want to be outside. And I also want to continue to expand on my problem-solving skills, just keep practicing critical thinking. Thank you, everybody, for coming and watching me, and special thank you to Dr. Woodbury for being my mentor. Does anybody have any questions?
How did you acquire so much background knowledge? from your mentors? Or
Yes.
Can you talk about how you were acquiring to be able to do the research out in the field, the lab?
There were times where I would visit and we just review all of the information, and it was kind of fun because a lot of the stuff that like physics, biology, chemistry, I got to see it all applied. So it wasn't just this useless information I was reading out of a textbook. I got to go to the research center and actually like use it, and so that was fun. So at times I knew more than I thought I would, but a lot of it Dr. Woodbury taught me just about what they were specifically working on.
You could talk about your project or your experience to a freshman or an eighth grader. What would you say to motivate them to follow in your footsteps?
You just kind of, it's a learning experience, and you learn, like, even though I was learning about antibiotics and antibacterial resistance and all of this, you learn a lot about yourself and what you enjoy and what you don't like. And so I think there's all this pressure to do these projects and know what you want to do for the rest of your life. But I would tell them just to try to focus on themselves, and yeah, I hope that answers your question.
Okay, one last question for me. What's the biggest error that happened to you during the project that you had to learn from?
It wasn't really, I was so guided during all of this that I didn't really make a mistake myself, but just as far as like learning things, I would, like the equipment I used, sometimes I wouldn't know how to use it, or I'd measure something too much. It was just small things like that, but it still was just a new experience, and sometimes I wasn't always comfortable, and so I think just overcoming my like fear was my like biggest mistake that I had to overcome.
I saw that video. I think it was an NCAPS video on the school website of you on the ATV.
Oh yeah.
That was pretty neat when you get a chance to see it.
Yeah, it was horrible. There were so many bugs that day. Yeah, I had to wear a helmet. Any other questions?
You talked a little about you found out what you liked and didn't like.
Mm-hmm.
What did you really like, and what did you really like, besides the bugs?
Well, like at the beginning of last semester, like I didn't know, and I just remember I kind of felt pressured to choose something, and I just chose this, and just learning, like when I go out there and do stuff, I don't know. I really like it. So, like all of it. I like being in the lab. I like being able to go out in the field. I really like being challenged and having to think about all this different information. So, I guess I just learned more what I definitely liked than what I didn't like, because I loved it. Okay.